Hello, everyone. My name is Chris Sensor with Siemens Digital Industries Software. I'm here with my colleague Pete. Say hello, Pete.
Hi, Chris.
Hi, Pete. And today we are going to talk about fatigue damage spectrum, also known as FDS, and how to calculate FDS with SimCenter Test Lab software.
Boy, that sounds exciting, Chris.
It's very exciting. It's one of my favorite little topics here, fatigue damage spectrum. Some of you out there may be familiar with shock response spectrum, or SRS, and the FDS calculation starts off a lot like SRS, but instead of using the absolute acceleration of a series of single degree of freedom systems, we use relative displacement for FDS. And we'll start off with some time histories in acceleration amplitude, as you can see here in the top part of my graph. And then we convert these to relative displacement from acceleration. And then we start counting cycles to get a histogram of cycles versus amplitude. And after we have this histogram, we apply what's known as Miner's rule to tally the total accumulated damage at each one of these single degree of freedom systems. And then we plot that total accumulated damage at the natural frequency of each SDOF system. And that's what we have in this graph down here below. These are the fatigue damage spectra from these time histories. Green is green, blue is blue, red is red. And then we have this pink trace here, which is the sum of all of these FDS spectra.
So at the end of the day, you could run a random vibration control test to try and hit that magenta line?
That's correct. This is a way for you to get vibration inputs from a number of different environments and combine them into a single environment to perform a vibration test so that your article under test, or your DUT, will survive those vibration environments. And there's two kind of techniques based on which of those goals you have, whether it's your DUT is going to survive all of the environments or just going to survive one or the other. And we'll talk about that more as we go on.
Yeah, I'd be curious if you could go through that calculation in detail, how you got to that exciting FDS plot in the end.
Indeed, we are going to go from soup to nuts here and start from taking time history all the way through calculating the FDS in these next couple of slides. So you're in luck, Pete.
All right.
So the first thing we need to understand when we're starting this fatigue damage calculation is this curve here. And this is called an SN curve, or a Wöhler curve, named after Herr Wöhler, a German fellow who did a lot of initial research into these failure issues that we have, particularly with trains at the time. But we've taken that and applied it to many different materials. And what this curve is representing is the number of cycles to failure of a particular material given the stress levels that are applied.
The amplitude of the stress level, that's the amplitude of a cycle, right?
Correct.
Not just the static stress.
The amplitude of one cycle of applied stress.
Okay, cool.
So to figure this out, we usually do this in a particular material testing device where there's a coupon sample of the material we want to generate this curve for. So there's three distinct regions of this SN curve. And we have this low cycle fatigue area, and this is an area where we have plastic deformation of our material, i.e., when you apply this stress, the material does not return to its original dimensions. Then we have this high cycle fatigue area of the curve. This is where elastic deformation occurs, i.e., when these stress cycles are applied, the material returns to its original dimensions. And then we have this last area of curve called the fatigue limit or endurance limit. It's also sometimes called the infinite life portion of the curve because no matter how many cycles you apply below this stress level, you will never cause a failure in your material. For FDS, we're really only interested in this high cycle fatigue region of the curve where elastic deformation is appearing. And this is plotted at the maximum stress level that occurs before material failure. And what we're interested in particular is being able to understand the slope of this curve. Now, you may look at this and go, okay, well, that's no problem. We have our typical linear relationship here, so slope is easy to figure out. Well, in reality, this is plotted on a log paper. So when you look at the linear curve, it's not a straight line. So to describe the slope of this in a log format, we use this equation over here, where we have these two breakpoints at the beginning and end of this high cycle fatigue region. So we have a pair for N2 and S2, so the number of cycles to failure at this stress level, and N1 and S1, the number of cycles to failure at this stress level at the beginning of the curve. And we can relate all of those with this exponent B, which we refer to as the Wöhler exponent. That all make sense, Pete?
Yeah, this Wöhler must have been a busy guy working on, was locomotive axles?
Locomotive axles. I think you might have been studying before the presentation, Pete.
Oh yeah, I'm all in, as you said, on the FDS.
Let's continue along here, and here are the steps for calculating fatigue damage spectrum. We've got some great pictures here that's going to help us to understand.
Nice pictures, Chris.
Thanks, Pete. Step number one, we have our lovely DUT here, some type of rover, and we've got an accelerometer on here, and our accelerometer is plugged in to a Scatus mobile chassis, and we're going to measure the vibration at this component of this rover. So let's see how that looks. Oh, we're moving, and we're getting some lovely data here. So that's step one. We've now measured an acceleration time history. The next step is calculating the relative displacement, and to do that, we need to create an array of single degree of freedom systems to do that. So let's see how that works. Pretty straightforward. All we're really doing here is figuring out what the natural frequency needs to be to adequately describe our fatigue damage curve. So each one of these systems, the natural frequency is equivalent to the square root of K, which is the spring stiffness over the mass of the system. And we can plot each one of those along the frequency axis. And for each one of these FDOF systems, we're going to use the same damping. So does that make sense, Pete?
Yes, that makes sense, Chris. So what happens to one of these FDOF systems?
So once we've set up this array of FDOF systems, for each one of these, we're going to take our acceleration time history and apply it as a base input to that system. So let's see how that looks. So we have our first FDOF system that we've created. And now we're going to apply our time history. That's going to cause this FDOF system to vibrate. And what we're going to look at is the response X minus the input Y. And that's going to give us this relative displacement response. And then what we do is we're going to apply that for each one of these SDOF systems in this array. So the first one, we get this relative displacement response. The second one, we get a different relative displacement response. And then we keep doing that for each one of these until we get to our maximum frequency of interest. And we get something that maybe looks like this response. So now we have all these relative displacement time histories. Our next step, as we mentioned, is starting to count the number of cycles. So what does that look like? Well, let's zoom in a little bit here and start counting cycles. So here's a portion of that curve, and this is a method called range pair, or a direct cycle counting method. And what we do is we start looking at half cycles from a peak to a peak, and we take that amplitude. And then we look at the next half cycle and take that amplitude. And we keep going through looking at each half cycle and measuring an amplitude. And then what we end up with is this histogram of range pairs, where we have each amplitude in relative displacement and then the number of cycles at each amplitude. Well, that looks pretty straightforward, right, Pete?
It does.
Pretty easy to take a look at a periodic signal and count the cycles there.
But I don't think every signal is exactly like that, Chris. Although the SDOF probably helps by isolating to a single frequency, but I think you could probably have more complicated responses.
Yeah, that's exactly right. So going through this series of SDOF systems is essentially applying a low pass filter to our input signal. But we don't always have nice signals like that. We sometimes have these crazy looking random signals, and this is a little more difficult to identify where we have a cycle and what the amplitude is. So we've got another method for cycle counting called rainflow counting. And how this works is, first we apply some hysteresis filtering to that time domain signal. So that cleans it up a little bit. It smooths the signal, and we only retain amplitudes that are outside what we call a gate range. So now that we have that signal smoothed, our next step is removing all the information except where we have samples that are reversals in direction. So you can see how that works here. All the intermediate samples were removed, and now we only have samples that go from one slope to another slope here.
Turning points sometimes, I think people call those.
Correct. That's another name for them, a turning point in the curve. And once we have all those turning points, what we do is further smooth the signal by binning these amplitudes. So what that means is we divide our displacement axis into a set number of bins, and then we move each one of these displacement values into the center of that bin. So you can see how we've now moved those samples, and now we have discretized this time signal into set number of bins, and you can see here the points that we moved a little bit to the center of that respective bin.
Just makes it easier to store the data in the end, I suppose.
That's correct. It makes it a little easier to apply kind of a blanket number of rules to determine what's a cycle and what's not. And the rules that we have for rainflow counting, the process, if you will, works like this. So we've taken our first 4 points here, and let's take a look. Are the inner points less than or equal to the outer points? It looks like it is, right? Now we're going to record that amplitude, okay? And that amplitude is going from bin 5 to bin 3, and we record this in the rain flow matrix. Then we remove those inner 2 points and connect the outer 2 points. And then we start over again from point 1. So now we have this number of points that we're looking at, and it seems pretty clear here that the outer 2 points are less than our inner 2 points. So what this means is, no, we do not have a cycle here. We move on to point number 2. And now we have 2 inner points that are less than the 2 outer points. So we have a cycle. So that goes into our rain flow matrix. And we keep going along this curve here. Is this a cycle? No. Is this a cycle? Yes. Because our outer 2 points are equal to the inner 2 points. So that passes our test here. So then we record this and remove it and start over again. No cycle here. Yes, a cycle here. Is this a cycle? No. Is this a cycle? No. Is this a cycle? Yes. Just keep going along here, finding cycles and recording that in our rain flow matrix until we have counted all of the cycles. And what we have is this rain flow matrix, which can also be converted to a simple histogram. Each one of these corresponds to a displacement, and you can take each one of these cells and figure out how many cycles, that's the number in the cells, 2 cycles from 5 to 2, and that can be recorded in a histogram like this. So now after we have this data, we'll convert from relative displacement to stress by this K constant, uppercase K, and that converts our amplitude cycles to amplitude in stress. So we still have cycles and amplitude, but we go from displacement to stress. It's important to note that this calculation is often referred to as pseudo damage because we have a linear relationship that is assumed between stress and the response. And also we need a precise SN curve for our fatigue damage spectra to have a physical meaning, i.e., when total damage gets to 1, we have a DUT that has broken. And again, as I mentioned here, from this rain flow matrix, the 2 values are subtracted from the from values to calculate the stress and convert this to a more linear histogram looking thing from a matrix.
Chris, why would we want a pseudo or fake damage? Is that still useful?
That is a great question. Yes. So even though more often than not, our FDS calculation is a pseudo calculation, it can still be used to compare inputs from 2 different environments on a particular test article. So you have environment A and environment B. You can still use this pseudo damage calculation, even though it's not perfect, to compare environment A and environment B and the effect that that might have on your test article.
Maybe it's more like a relative damage. I can see which one of those 2 environments is more damaging, and then that helps me design my part. If it can survive the more damaging one, it should be able to survive the less damaging one, I guess.
That is a correct assumption, yes. So yes, sometimes we call it pseudo damage, sometimes we call it relative damage, and in the end, the comparison works as long as we apply the same constants to both calculations. So now we've gone through step 4 and counted cycles. We move on to step 5, which is to apply Miner's rule. So how do we do this? Well, Miner's rule is that you take the number of cycles at a particular amplitude on your test article and compare it to the number of cycles to failure from your Wohler curve. And then you do that for each one of these histogram bins and sum them all up, and that will be your total damage. That is Miner's rule in a nutshell.
If I can understand better, lowercase n is from my measurement, my acceleration time measurement converted to displacement, and uppercase N is a property of my test article, the material it's made from.
Correct. And,
Okay.
and is a property of your Wohler curve, and small n is a property of your measured
signal
data. So what we're doing here essentially is taking this stress number of cycle pairs from our histogram. We find out where this point at this stress level is on our Wohler curve and take the number of cycles to failure from the Wohler curve. So now we have the number of cycles at the stress level over the number of cycles to failure at the same stress level. And we keep doing that for each one of our entries in our histogram or rain flow matrix. And then we start summing those all together. And this is our total damage for the SDOF system that we're using for this calculation. And now after we have the total damage for this SDOF system, we move on to the next FDOS system and apply the same calculation. And then what we end up with is a total damage number for each one of these SDOF systems that we've created. And we plot it and then connect the dots. And this is our fatigue damage spectrum.
So a different amount of damage per frequency. I guess that's good if we have certain resonances or whatever in the environment to be able to vary that.
Yeah, we could take a look at our test article and understand where critical frequencies are and try to figure out a way to either move those frequencies to a less damaging area of the curve, or design some stowage procedures or some packaging that's going to protect our DUT from these damage cycles. We went through this calculation. In reality, we pretty much do all these steps at once with this equation here. We have our stress displacement constant, that's a material property. We have our Wohler exponent B, which is from our SN curve, and our Wohler constant A, which is also from our SN curve. In order to describe this line, we have some constant A to the exponent B, and then when we plot that in log-log plot, we get a straight line. We do this calculation for each one of these Miner's pairs, we call them, in our histogram. So if you look back at our histogram here, each one of these entries in the histogram, each one of these bars is a Miner's pair. And then we have lowercase n, the number of cycles in the Miner's pair, and z, the relative displacement of the Miner's pair. So all this gets run through this equation, and we end up with a single number at the end for the damage amplitude that's going to be in our fatigue damage spectrum. So let's take a look at how this is done in SimCenter Test Lab. So we're going to go into Test Lab 2206, Test Lab Environmental, and we're going to go into Mission Synthesis. So we'll start a new project here.
Hey, Chris, can you use Test Lab tokens to run Mission Synthesis?
That's a great question, Pete. Yes, you can use test lab tokens for mission synthesis.
Oh, cool, because I already have tokens, so I'll be able to run this.
Absolutely. So we can go right into the mission synthesis workbook here. And the first thing you'll see is the software wants you to save before it starts doing all of its stuff. So it'll come up with a save as, and we'll just pick a file name and save it. I'm just going to save over something I already had. And you can see our interface here. We have our navigator on the left, and then all of our mission synthesis stuff on the right. So let's pull in some data here. So I'm going to go into SimCenter, test lab data, and I already have some data in here. So we'll find our throughput data, and we're just going to add this into our workbook here by clicking on this icon here to create a new environment.
Really good icon designers. You want to add data, you hit a plus symbol.
That is probably the best way to go, just my humble opinion. And let's do something else fun here. We can go in and add some shock data as well. So let's take a look. Here we have some shock data we can add. So the next thing we can do is just display all of this. And we can see here, we'll hit Control and left click, display size, and maximize this. So we can see the time histories. We've got a nice shock event here. And then we have our other time histories here. This is from a car, an electric vehicle actually, that's going over a test track, and a couple different environments there. So this blue trace is a normal kind of accelerate brake. We have the red trace here, which is sawtooth data, we can see here. And then we have this green trace, which is Belgian block. And then, of course, our fuchsia trace, which is our shock event.
I thought the potholes where I live were pretty bad, but those Belgian blocks look pretty rough.
They do, don't they? So let's go back to our regular display here. And we have all these highlighted. And what we're going to do is calculate our FDS for each one of these environments. So we hit this button up here, excitation to MRS FDS, and it's going to come up with this dialog where we can start plugging in some material properties that we discussed before. By default, we've got our Q factor and damping, which are linked to each other. So if I change damping, it's going to change my Q factor. If I change my Q factor, it's going to change my damping.
Yeah, they're like the inverse of each other, huh?
They are. It's actually the equivalent is one quantity is equivalent to 1/2 times the other quantity. You can see we're calculating away here. And now we have the SDF calculated for each one of these environments. And there is a little check mark that happens in the cell here to let us know that we have an FDS calculated here.
And I see if you hover over it, it also tells you what the calculation was to get that FDS.
Correct. It tells you all of the different constants that were used in the calculation, as well as the cycle counting method. In this case, we used a direct cycle counting method, range pair. And now what we can do is hit display curves again, and we can see our time histories, our maximum response spectrum, our MRS, and our FDS. MRS is calculated exactly like SRS is. So the MRS of the shock pulse will overlay with an SRS
I
pulse.
saw you zoom in on one of those graphs, but can you make this area a little bit bigger relative to the top? There's a lot of gray area there.
Yeah, so I can come in here and I can move this up a little so we can see a little more of our curves, and then I can hit Control and right click and display size and maximize all of our different FDS curves as well. So you can see for each one of these, we have sawtooth, Belgian block, accelerate brake, and you would assume from the time history, this accelerate brake has the lowest amplitudes that would also have the lowest FDS. So now let's do something else here. We've got each one of these, but this is for just one cycle. Let's say in real life, we might experience this event 10 times, this event 20 times, this accelerate brake, maybe we'll see that most of the time, maybe 100 times. And this shock event, maybe we'll see that 250 times or something. You hit this pothole and get this bad shock on your car. Now we can hit Shift and highlight all of these, and what we're going to do is hit this button here, apply number of repetitions, and now this takes our FDS, and you can see, let's see, we're 1 to the -9. Now if we display this again, we'll see how that has shifted all of these up.
I see for the first recording, it's 0 to 12 seconds. So a repetition of 10 means this would be as if it was exposed to 120 seconds of that vibration total.
Correct. That's exactly right. Now for the shock event, since we just had one event in that time history, we also are basically saying, okay, we're going to repeat that shock event specifically 250 times to get this result. All right, so the next thing that we can do is say, all right, well, I have all of these events. Now, in the case of a car driving down the road, perhaps this is equivalent to some type of sum happening, right? We're going to experience each one of these things in a lifetime. So we're going to do a sum and display that. And we can see if we have all of these environments, we're going to have an equivalent FDS of this cyan trace here. Now you have another scenario where maybe your test article is only going to be exposed to one of these environments, but you don't know which one it's going to be in. So what you do is design your test article to survive all of these environments, but not in sequence, just one or the other. That would be this envelope FDS here. So we can apply that and see what this looks like. And now, in this case, our sum and our envelope are pretty close to each other. Let's just take a look at both of these, and we can see, we zoom in, they're really pretty on top of each other here. But just for an example, let's make a copy. Let's say this sawtooth here. And we're going to do 2 equivalent traces to just see how this works if you have 2 traces that are similar to each other. We're going to calculate the FDS here again using the same numbers. And if we display these, we can see, yes, they're on top of each other. But now we'll take the envelope and the sum here and display those. And here we can see what you might expect. Our envelope is right on top of our combined curves, but our sum is some amount higher than our source curves.
And that's because that y-axis is in a log scale, It's not like a linear sum, I guess.
That's
Why I
correct. It's
look like
like adding dB, right? Where if you have two sources that are 100 dB, 100 dB plus 100 dB isn't 200 dB, it's 103 dB. The same type of phenomenon here. So that is our demo of calculating fatigue damage in mission synthesis. Again, my name is Chris Sensor. Feel free to reach out to me. My email is chris.sensor@siemens.com. You can also reach me at LinkedIn. And of course, our Siemens community site is a great source of information for all your vibration testing needs. And you can look there for our FDS article that is a companion to this video. Thanks everyone for listening and hope to see you soon.